Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Okay, lecture 89. We're going to talk about longitudinal waves. So, that's a big word, right? What do you think a longitudinal wave is? Remember, before we've talked mostly about transverse waves. Transverse wave is where the velocity of the wave and the direction of the motion is orthogonal, right? So these transverse waves, we have something oscillating up and down, but the wave is traveling this way, right?
Yeah.
Yes? So longitudinal waves are where the displacement, right, the motion is actually in the direction of the wave velocity. So sound waves are kind of a classic example of this, all right? But it's going to take a little work to get through. But where I want to start is with just a quick review of oscillators and springs, right? So if I imagine a mass on a spring like this, right? Recall that we can talk about this in terms of the force and the displacement, where this displacement I speak of, we'll call it x, is the deviation from its equilibrium position, right? And if I were to take this mass and pluck it, right, it's going to oscillate back and forth. But if I just pull on it, right, it's going to resist my pull in the opposite direction, right? So if I pull down, it's going to pull up, right? If I push in, it's going to push back, right? And so we got this this Hooke's law: force equals k times x. It's really minus k times x to indicate that it's pushing in the opposite direction that you're trying to move. Okay? But you probably also remember that we could look at this from an energetics point of view. So I'll write U for the potential energy. Again, x on the x-axis, and we'll get this parabola like so, where this could be the amplitude of this oscillation that I'm talking about, right? This is negative a. There we go. So we can imagine the ball rolling in the well back and forth like this, right? That represents the oscillation, yes? And so here the potential energy, U, was equal to 1/2 mass omega squared times x squared, right? And so we made this connection between the spring constant k, which I'm going to call k sub s, because we're going to use wave number or wave vector in this lecture to talk about a wave that's 2 pi over the, 2 pi over lambda? Yeah. Or lambda over 2 pi. No, it's 2 pi over lambda, right? So we can make this connection between the two, right? And write that, ks, the spring constant, is equal to m omega squared, right? Yes, this ringing a bell from the discussion of simple harmonic motion, right?
Yeah.
The x position of this as a function of time would be the amplitude times the cosine of omega times t plus some phase constant delta, right? This would be dependent upon the initial conditions, right? If we just started from some fixed position, amplitude a, and released it, delta would be 0 and t equals 0, right? So you remember all of this, right? So what if I want to replace this spring? Instead of a spring, I want to consider a rod. So here I've got a rod. You can think of it as a thick wire if you want to. And I'll, again, suspend a little mass from it like so. But this is a rod with some cross-sectional area. Call it A, right? And of some length, call it L, all right? And it's a solid, right?
Yeah.
And if we were to talk about F over A and X over, I guess we call it delta X, right? Where now it's not so clear what is X and what is delta X here, but let's call this X over L. And we would still get a curve that looks like X, but we would call this stress, and we would call this strain, right? And the force we would define in terms of the ratio of the stress divided by the strain, which is called the Young's modulus, right? So the Young's modulus, which I write as the capital Y, right, with the capitals on it, is equal to minus. The stress is force divided by area divided by the strain is x divided by L, right? So I can rewrite the force in terms of this. That's going to give me x over L times, actually I want to pull the x out to the side. I want the x to be over here. Put the area up here, minus sign force, and then we have the Young's modulus here, right? So I'm going to put parentheses around this term right here. Yes? So I can think of Young's modulus, right, written out in terms of the force. This is really kind of like the spring constant, Ks, right? This term here. Because for the spring, we had F equals minus K times X. And here I have F equals minus some stuff times X. Call this stuff the spring constant, right? So we can kind of say that the Young's modulus is kind of proportional to the spring constant for this is proportional to the Young's modulus, right? So we can make this connection. K sub S, the spring constant, is equal to m omega squared. Now why am I doing that? Because I want to now think about a traveling wave, right? Remember, that's a little bit different, right? And with a traveling wave, we have this relationship, right? So if we think of a traveling wave, let's say, I want this to be x, I want this to be, something, random variable y. And we've got some wave like this, right? And I say, well, the distance from peak to peak, we call that the wavelength, right, lambda. Okay, and the time it takes, if I were like to stand right here and watch as this wave rolled by, right, the time it took for this peak to arrive here, we would say that happened in a time big T, which we call the period, right? Yeah. And so I can say, well, whatever this is that's moving, because it's not matter, right? Whatever it is, it's a distance lambda has gone by in a time big T, the period, right? Remember that? Yes. Yeah. Okay, well, we can relate this to, I can rewrite this as omega over k, where k is this wave vector, or wave number, okay, in one dimension. So omega is 2 pi over the period, okay? We call that the frequency. And k is 2 pi over lambda is equal to k, right? It's just a different way to write it, yes? So we can write this down. Now let's say, well, let's let this oscillation frequency, what if that oscillation frequency was the wave frequency of the traveling wave, right? What would that look like? So, I mean, it's not clear that it should be that, right? I mean, what I've talked about here is just simple harmonic motion. This is a mass on a spring, or a mass on a rod, which is behaving like a spring, okay? I mean, I'll kind of give you the scoop that it's not going to be the same, right? Rods, if I have a steel rod and I hang a mass from it and pull on it, you're not going to see it going up and down like this, right? Any motion it's going to have will be very tiny, okay? It's a really tight spring, okay? And you know this because you've probably picked up a steel rod or a steel bar of some kind and you try to pull on it. You notice it doesn't pull like a spring does, right? But it does on a very small scale, okay? And that's what we're going to be talking about today. So I'm saying, let's treat for a moment the spring constant, right, the simple harmonic motion. Let's say that this frequency that we naturally get from simple harmonic motion, let's try to relate it to the wave frequency and see what we get, okay? So I want to see what would the velocity be if this omega and this omega were the same thing, right? So if that natural frequency of the rod for simple harmonic motion happened to be the wave frequency, okay? So for the spring, so I'll write this over here, V equals lambda over T, which equals omega over K. So I'll need this room here. So for a spring, that's this system here, what will we get? We get that the velocity was equal to omega over K. We're going to write K as 2 pi over lambda, okay? And then we have, of course, the omega term, but omega is the square root of the spring constant divided by the mass, right? So if I solve for omega here, right, and take the square root, I get that it's equal to the square root of the spring constant divided by the mass. Okay? And we can say, well, this is proportional to some constant c times the square root of the spring constant. Okay? So this constant reflects this mass term, this wavelength term. I'm not even sure what it means in this context. Okay? So for the rod, what would this look like? We'd say V is equal to 2 pi over lambda times the square root of K, the spring constant. Well, we said the spring constant is this thing here. So that's A times the Young's modulus divided by L. And then, of course, divided by the mass. So what is the mass? So 1 over the mass. Well, for a rod, the way we usually do it is we say, well, we take the density of the rod, so we'll write density. Right? And to turn it into a mass, we have to multiply it times the cross-sectional area, call it A. Right? And some length, we'll call it L. Okay? So we get L. And so you see some stuff happen. See, we get some cancellation with the area, right? The L gets squared, right? So we'll have y over L squared. We can go ahead and pull that out, right? So we write that as 2 pi over Let me get to this. This is wrong. Sorry about that. This should be lambda over 2 pi. Lambda over 2 pi. Lambda over 2 pi. Sorry about that. So I'll write this. Lambda over 2 pi times L. Because I just pulled the L squared out of the square root, right? Times the square root of the Young's modulus over the density. And so this, we can just say some constant C, or not equals to, but what proportional to, some constant C times the Young's modulus over the density. Okay, that's interesting, right? So that's effectively what we would be looking at. We might remember that for the string, and we got that for the string, it was the square root, the wave velocity was the square root of the tension divided by the, what do we call it, linear density, the line density. Linear density is the mass per unit length of string, right? Yeah. So we use the symbol mu for it. So the tension divided by mu, square root of that is the velocity. And so this seems similar, all right? So it seems promising. But let's do it formally, okay? So this is all just kind of equating simple harmonic motion to traveling waves, right? But we haven't really said how that would work yet. So that's what we're going to do now. Okay, so let's imagine that we have a steel rod, okay? And we want to focus our attention on this little delta x, this little bit of the volume of the rod, right? So that's some length in this direction, right? We'll call that delta x, but that'll have associated with it a volume, right? That delta x times the cross-sectional area, right? So it's that bit of mass in the rod. And I want to imagine I have a hammer, okay? And I want to swing that hammer at this rod, okay? So after it impacts, what happens? So the hammer strikes the end of the rod, right? Yeah. And we can imagine that there's some momentum and energy going in that direction, yes? So what happens to the rod? I haven't said anything about whether the end is fixed or not, but let's say it wasn't fixed. It was just on the table or something like that. What's going to happen?
It's going to get pushed back.
Yeah, it's going to get pushed, right? Yes, after the hammer impacts, right, the rod is going to move, yes?
Yes.
Now, something else is going to happen though, right? It's not going to move instantly, okay? There's going to be a little bit of compression in the rod. And that compression is going to move through the rod, kind of like a wave, right? So the little compressed region is moving its way through the rod, right? Until it reaches the end of a rod, or continues going off to infinity if it's an infinitely long rod. Whatever, right? But so this is this longitudinal wave that is propagating across the rod, okay? And if we were to think about, well, what's the rod made of? We know what it's made of. It's made of atoms, right? Yes. And so if I were to represent like the rod by the atoms, right? So here's our, one layer of the atoms in our rod, all equally spaced. This is before the hammer hits. So we'll find that after a while, if this wave continues to propagate through, and especially if we had repeated hits, that there'll be a region, right, of compression here. I'm actually going to center on it, let's say here. And another region of compression here, right? This is our wavelength, okay? Before we went kind of crest to crest. Well, this is a crest in the sense that it's a peak corresponding to the pressure there, right? Or the density. The density has increased a little bit, right? Yeah. Things have gotten kind of smooshed together. And I know we said that solids and liquids were incompressible, but they compress a little bit, okay? This is actually what makes the speed of sound so fast in a solid or a liquid, right? Solids compress much less than liquids do, and the speed of sound is very fast in a solid, okay? If you've ever put your ear to the railroad tracks, right, to listen to the train in a great, great distance, you can spot it long before you can if you don't put your ear to the tracks. It's the old bank robber or train robber trick. Because the speed of sound in steel is very fast. Do you get the idea, though, of these, like, there are also some regions that are not just normal spacing, but they're actually rarefacted, which means that their density is a little bit greater than it normally would be, okay? So this would be less than what we had drawn before, okay? So, dense regions, so these would correspond to the troughs, okay? I'm not going to attempt to draw a sine wave. Oh, I guess I could, right? You have peak going up here, minimum, and then back up here, you're back up to the peak again, right? Something like that. You see the correspondence? Yes? Okay. I'm going to come back to the hammer and the rod, but first I want to review the string again. I want to show you another way to come up with a wave velocity for a string, okay? And then we'll use that to come up with a wave velocity for both sound in a solid and sound in a liquid, all right? So revisiting the string for just a second, I want to imagine that I've plucked a string a little bit. So here's my string, and I've plucked it by pulling upwards with a force, call it F, okay? There'll of course be tension in the string. And I know you're saying, oh, why isn't the tension going in this direction? Well, because the tension is in this way, right? So this is a string attached to some wall in the distance, okay? I'm not worried about the attachment point. But I have displaced it by applying a force upward, okay? And I want to call U delta t. This is the speed, the average speed, right, with which I plucked the string upwards. And this disturbance that I've created in the string, right, as time goes on, this will go out farther, right? It's traveling at the speed v delta t, right?
Yeah.
So you can see that the ratio of F over t, right, is going to be proportional to U delta t over v delta t. And we use the trick of using a ratio so that we can turn proportionalities into equalities, right?
Yeah.
Delta t is common to both of them, so we can cross that out, right? And so we just end up getting that F over t is equal to U over v, or F is equal to U over v times t, the tension in the line. Yes?
Yes.
And do you remember what an impulse is? Force times delta t, right? And that this is equal to the change, let me write it as delta momentum. Okay?
All right.
So what's the change in momentum? Well, before, this string was not moving upward with velocity u. Now it is, right? So it's m times u. But this is a string, and m is going to be measured in terms of its line density, right? So I can replace m with mu, the density, the mass per unit length of line, times, we'll just call it delta x, okay? So that's this distance here, delta x, all right? And then, of course, times u. Don't be confused with the mu and the u here, right? F, I'm going to use this expression here, right? So I'll replace this F with u over v times t, u over v times t, the tension, times delta t, the time, okay? Does that make sense?
Yes.
Also, I think I want to replace this delta x with v times delta t. This is delta x, right? This distance right here. Do you see that?
Yeah.
So this delta x is just v delta t. So I have u over v times t delta t equals mu, delta x is v delta t times u. Delta t's will cancel, right? Because they have the same time interval. Also, the u's will cancel. I have u on this side, I have u on this side, so I can get rid of that. It's 1 over v. And I'm left with 1 over v times t equals mu v. So multiply both sides by v, will give me v squared. And so I'll get that v squared is equal to t, the tension, divided by mu, the linear density. Okay?
Okay.
If I take the square root of that, this velocity is the velocity of the wave speed that we talked about, I think, the lecture before last, right?
Yeah.
So this is the method that we got. It's pretty straightforward. Just use impulse is equal to the change in momentum, right? And we should be able to extract a wave speed, yes?
Yeah.
You see how that works?
Yeah.
Okay, so now we have to set this up for the rod, and that's a little bit trickier. Okay, so after the hammer hits our rod, the end of our rod will be moving with a velocity of u, okay? I'm going to actually extend this wall just a little bit so I have a little more room. So this distance here will be u delta t. You see that?
Yeah.
But I want to consider this some delta x, right? Some portion of my rod going up to this point right here, right? And this, of course, will be moving with some velocity v. This is the wave velocity. This is that wave we hypothesized would propagate through the rod after we smack it with the hammer, right? And so this distance here would be v delta t, okay? So the volume is going to be equal to the cross-sectional area times some distance L, right? But this distance L is just this v delta t here, right? V delta T. So this is the volume element we're considering. This little volume element right here. The cross-sectional area is a constant on this rod, and so we get this. Now, what about the change in volume? So what is the change in volume? I'll call this, I'll use capital V for volume, because we sometimes use V for other things. I'll put capitals on it so that it is our volume. That actually looks a little funny. Let's take that off the bottom there. What's the change in volume look like? Well, that's this little bit right here, right? It's going to be negative for starters because it's compressing, right? As we smacked it, it's kind of, everything's getting smushed together. And this will be, again, the cross-sectional area times this little, call it delta x if you want, right? Delta x, but that's just minus a times u delta t. See that?
Yeah.
So if I divide these two, right, what do I get? If I divide the change in volume by the total volume, this will be the same thing as minus a delta x over a times L. The a's will cancel, right? And this will be equal to this term here. A over minus a will also be minus. We'll get V will be u delta t. The delta t's will cancel as well. You can see that, right?
Yeah.
Over v. And so these minus signs will also cancel. So delta x over L will be equal to u over v. Okay?
All right.
That'll be useful for us in just a minute. Now I can do this step where I talk about the impulse being equal to the change in momentum. So the impulse again is F delta t. The change in momentum is just the mass m times the velocity u. But the mass I can rewrite as the density times the volume, right? So that will be the cross-sectional area times the volume here would be this L, right? Call that this L term, yes?
Yes.
And then, of course, times the velocity u. F we want to write in terms of the Young's modulus, okay? So we have to recall, what does Young's modulus say the force is? It says that the force is minus a delta x over L times the Young's modulus, right? This we had from before. This was our, this is our spring constant, right? Well, really, this, and this are our spring constant. This is our delta x, right? That's the displacement. But if I substitute that in over here, I'm going to get, I'm not going to worry about the signs too much, right? The negative sign. A delta x over L times Young's modulus times delta t equals this L, right? We said, well, that was just V delta t, right? So let's just replace that now, right? V delta t, right? That's this distance here, V delta t. You can see the delta t's are going to cancel, so let's get rid of them. Like that. Delta x over L, right? We already have an expression for this. This is u over v. So let's replace that here with u over v, right? That's coming from this relationship here. U over v. And the areas, they're going to cancel. Got an area here, an area here, so let's get rid of that. Yeah? Still looking good? So we have u over v times Young's modulus equals rho v u. Why do I have too many equal signs here? Rho v u. Cross multiply by v. The u's will cancel. You see that's going away, right? That's gone. And so what do we get? Cross multiply by v. We get that v is equal to Young's modulus divided by the density. Take the square root of that. There's our velocity. Okay? Very similar to what we got with tension, and also similar to what we kind of got phenomenologically when we thought about oscillations in a rod, treating it like a mass on a spring, right?
Yeah.
So this is our wave speed for a solid, okay? So you could use that to, for example, calculate the wave speed on the railroad tracks if you have the Young's modulus for steel. I don't actually have that with me, so I can't do that for you now. But does that make sense?
Yeah.
Okay. So let's look at how to modify this. Actually, to do it for a liquid or gas is not that much different. Gases get a little more complicated, but virtually the same kind of things go into place for liquids and gases. Okay? But instead of Young's modulus, we're going to use the bulk modulus. Okay, to consider this same situation of these longitudinal waves propagating through either a liquid or a gas, both are fluids, we're going to think of a cylinder with a piston, right? So this is not a rod anymore. This is now a pipe, if you will, okay? And we have a piston. You know what a piston is?
Yes.
Yeah. Think about it. If you don't know what it is, think of a push pop, right? Push the ice cream up. Right? So we have a piston, so we can apply this, instead of a hammer, we're going to push the piston in rapidly, okay?
All right.
And that will impart some velocity u. So it's virtually the same setup that we had before. This little bit of displacement that we get from the piston push is u delta t, right? And we're going to hypothesize that a wave is going to propagate through this with speed v, right? So this distance here will be this volume element delta x, which is moved because of this wave speed, right? So v times delta t is this distance here. The formulas for the volume are virtually the same, except we won't use the length like we did last time. So we'll say the volume is equal to the area times v delta t. That's the volume element that we're interested in. And that the change in the volume, put the capital sign again, will be equal to minus a u delta t, right? So the relevant quantity for us here is going to be delta v over v, right? And that is going to be equal to u over v, or minus u over v, rather, okay? Because the a's, the areas cancel, and the delta t's cancel, right? Yes? We'll again use the same trick. Impulse is equal to the change in momentum. The impulse, which is the f delta t, right? This is the m times u, right? So what is f delta t? Remember the definition of pressure?
No.
Pressure is force divided by area, right? If I apply a force over a given area, the force per unit area is the pressure. So we're going to call this, I'm going to call it delta P because it's a change in pressure, right? Delta P times A, that would be equal to the force, right? If I take the change in pressure and multiply it times the area, this cross-sectional area, then I'll have the force that's imparted, right? This is from the piston. You still have to multiply times delta T, though. So I'm replacing F with delta P times A. I'm going to replace M with rho, the density, times the area, times v delta t. That's this volume element, right? Then times u, because it's momentum. Mass times this velocity u. That's the change in momentum, right? So we see we get some cancellations. The areas cancel. That's nice. The delta t's cancel. That's good. And so we get that delta p is equal to rho v u. The bulk modulus, which we really didn't talk about, but it's totally analogous to the Young's modulus, right? The stress over the strain, except this time the strain is given in terms of the change in volume, right? Before it was, for a rod, the Young's modulus was the change in length divided by the length. That was the stress, or the strain. This time the strain is going to be the change in volume divided by the volume, right? So the bulk modulus, which is called B as a label, right? It's going to be equal to, again, a minus sign because it's always opposite of the change, right? Just like Hooke's law. It's going to be delta P divided by delta V over V. Okay? So we can solve this for delta P. Again, I'm just going to ignore this, the signs, the negative sign. So we can replace this with delta V over V times B, right? So delta V over V times B, and that's equal to rho V U. But delta V over V, we know what that is, right? That's this minus U over V term, right? That would, of course, take care of our signs from here. But we're ignoring that. So let's replace delta V over V with this relationship, U over V. We get U over V. The U's will cancel just like they did in the last example, right? That's 1 over V. We can cross multiply by the velocity. Gives me the velocity squared on this side. We can solve for it. And we'll get that V is equal to the square root of the bulk modulus divided by rho. Okay?
Okay.
So before, for the rod, we had that it was the wave speed was proportional to the square root of the Young's modulus divided by the density. Here we have that it's proportional to the bulk modulus divided by the density. Okay? So not unsurprising. This should be similar to what we had before, right? And this applies to both liquids and gases. Okay?
Okay.
Now Newton, I think, was probably the first person to do this, but he actually got it a little bit wrong. Okay? And we're not going to be able to get into the the nitty-gritty details of this because that would require thermodynamics, and we haven't done that yet. That's going to be the, the start of the next section of this course, this lecture series, which will be thermodynamics. But we can go through it a little bit. Okay, so the wave speed is equal to the square root of the bulk modulus divided by the density, but the bulk modulus is the bit of trickiness, right? And so when we're talking about liquids and gases, we need to take into account thermodynamics, because when their volumes change, the pressures change, the temperatures change, okay? This is not something that we have to worry about so much with solids. So there's different bulk moduli, that's the way we say it. Newton had assumed that the correct one to use would be the isothermal. What does that mean? That means that the temperature doesn't change, but the bulk modulus, the isothermal bulk modulus you can show is just equal to the pressure, P, okay, of the liquid gas, or liquid or gas, okay? So if that's the case, then what does that mean? That means that the wave speed would then be just the square root of the pressure divided by the density. And he tried that and got an answer that was about 20% too small, so it wasn't fast enough, right? And I think he may have thrown in some fudge factors to try to fix it, but in the end the problem was that he used the isothermal bulk modulus, okay? The correct bulk modulus to use is actually the adiabatic bulk modulus, which means that the adiabatic means that no heat is transferred, okay? But whenever you create a sound wave, there is a change in temperature inside the wave, if you want to think of it that way. So you cannot use the isothermal. Instead, you want to use the, I'll put this over here, implies V equals the square root of P over rho. The correct bulk modulus to use is the adiabatic bulk modulus, which is some factor gamma that depends on the gas or liquid that you're talking about times the pressure. So it's not that much different. I mean, this you could argue was Newton's fudge factor, right?
Yeah.
But he didn't mention that he was doing it adiabatically. So gamma for air, for example, is 1.4, okay? Now this is not all that useful yet, because this, of course, says that V is equal to the square root of gamma P over rho, which is lovely, except that, well, what's the pressure P? So here we can use a little thermodynamics, and you've probably heard of it from chemistry, right? The ideal gas law. Right? What does it say? It says that the pressure times the volume is equal to the number of moles times the gas constant times T, where T is the temperature in kelvins. Right? All this we will talk about when we talk about thermodynamics, but you've probably seen a little bit of it here, so I will just substitute some of this stuff in. Essentially, if we solve this for pressure, right, we would divide by the volume, okay, like so. Yes, now we have something that we can substitute in for pressure in terms of temperature and volume, right?
Yeah.
But we can actually make a substitution and write this out in terms of the density times the gas constant times the temperature divided by m, the molecular mass. This is the one that you remember from chemistry, right? This gives you the number of grams per mole.
Yeah.
Except, we do in physics, we always do things in SI units, so these would be kilograms per mole you'd have to use there. Okay? So we can do a simple calculation for air, because now we have that the velocity v is equal to gamma p, which is rho RT over m, but this is the same rho as the density in this velocity formula, so the rho's will cancel, and we'll just get gamma RT over m, the molecular mass. Okay? So if we say, well, what's the speed of sound in air? Right, so gamma will be 1.4. It's 1.4. The gas constant is 8.31. That's a joules per mole Kelvin, okay? Times the temperature T. Well, the temperature T has to be in kelvins, right? And so the way that you convert Celsius to kelvins, well, if you're in Fahrenheit, you want to go, so like 68 degrees Fahrenheit is 20 degrees Celsius. The easy conversion, 86 Fahrenheit equals 30 Celsius, and 68 Fahrenheit equals 20 Celsius, right? So if you ever have to do Fahrenheit to Celsius conversions, that's an easy mnemonic to remember. Do you see the relationship here? 6.8 and 8.6, and they're just flipped, right? The Celsius temperatures differ by 10 degrees, okay? So, but we're interested in 20 Celsius, right? What we call room temperature. That's 68 degrees Fahrenheit. But kelvins, this is a different temperature scale, and we'll talk about it when we do get to thermodynamics. And the definition of the Kelvin scale is you take the Celsius temperature and add 273 to it. Okay? So where the 0 on the Kelvin scale corresponds to absolute 0. It's the lowest possible temperature. Okay?
Okay.
So the temperature, 20 degrees Celsius, is going to be 293 kelvins. Okay? Divide by m. So now we need to know, well, what is the molecular mass of air? All right? And the molecular mass of air is 29 grams per mole. So that's 29 times 10 to the minus 3 kilograms per mole. So we'll have to divide that by 29 times 10 to the minus 3 kilograms. Well, I'm not going to write the units. I didn't write the units for the other stuff. Okay, and so punch that into the calculator for me, maybe Gabriel, and tell me what we get as an answer. So 1.4 times 8.31 times 293 divided by 29,000. Oh, no, I'm sorry, not 29,000. It's 10 to the minus 3, sorry. So that'd be 0.029, right? What do you get? And then take the square root of that. What do you get?
342.85.
Good. It's about 343. And the units, of course, since it's SI, will be meters per second. And that is the speed of sound in air at room temperature. Okay. Any questions so far on these longitudinal waves? You get the idea of the compressions and the rarefactions. It's, you know, the transverse waves, they look like waves. Right? You see them, they're kind of waving like this, up and down, right? They do it in space and they do it in time. Sound waves and other longitudinal waves are not so easy to see. But you get the idea, I think, right?
Yeah.
Okay. All right, well, let's call that it then. Okay?